Welcome to day 44. This says connections between the graphs of f prime, and f double prime. You might remember we're in the middle of topic 4 applications of derivatives right now in our AP Calculus AB course. And last class was really all about using f prime, and f double prime to create the graph of f. But we should remember that calculus always talks about gnawing, right? That acronym GNAW, gnawing on a concept where you approach it from 4 different viewpoints. And the viewpoint we're going to focus on today is graphically. Now, you might say, well, wait, we just did graphing last class. I would actually argue that last class we were much more of an algebraic approach. We had equations. We did calculus and then algebra with the equations. And yeah, at the end, we did create a graph. And although we're pretty darn good, I think, at this point with graphs of f, what we haven't looked or talked about yet are what do graphs of f prime and f double prime look like? And how do they help us see characteristics of the graph of f? So today is all about graphs, but very little about equations. In fact, if you look through this entire packet, there are very few equations. I think there's only one little small set of equations one time. But we're still going to be using those relationships of critical points, inflection points, and all we're going to do is just get better at them. So let's begin. Our goal here is to match the graph of f, and notice there are 4 graphs in the left column, to the graph of f prime. Now, although I said there are really no equations here, I am unfortunately going to start with one equation because I think it's really going to hammer home a couple of things. And I'm just going to start with this equation on the upper left. The equation on the upper left looks quite linear. I'm going to make the assumption that it's linear. And it also looks like I could even calculate the slope pretty easily. It doesn't look like it goes down 2 over 1, y-intercept of 0. I'm going to make the bold assumption that this equation is in slope-intercept form, negative 2x plus 0, or just negative 2x if you'd like. Now, if I wanted to make an input-output table here, if I wanted to look at x comma f of x, we could, of course, plug in a few x values, and they'd give us f of x values out. And let's try a couple. Let's try negative 1, negative 2 times negative 1 is 2. We'll try 0, that's 0. And then we'll try one more. We'll try 1, which gets us negative 2. And, of course, these correspond to points on this graph. Nice. Well, it's not too hard here to make the connection to the derivative of this graph, where the derivative, of course, will be f prime. Derivative of negative 2x is negative 2. If I made an input-output table, we should be able to create the graph of f prime of x. Let's use the same inputs, negative 1, 0, and 1. Well, it tells us the output, regardless of the input, is always negative 2. So we have this. And of course, this gives us 3 points as well. The point negative 1 comma negative 2, 0 negative 2, and 1 negative 2. And I think looking down at the graphs, it won't shock you too much to see that this matches D. And here are the 3 points that we plot here on this graph of f prime of x. Now here's where things get tricky. What do these points mean? Well, if we just focus on this point here, 1 comma negative 2, we need to remember that this point is in the form of an input x and an output f prime of x. And so what that's telling us then is x values on any graph are always going to be the location where something happens. Now the what happens is all about the equation we're dealing with here. So the way that I would interpret this point that I have the arrow pointing to is at an x of 1, and I'm going to write 2 sentences, and you can write them if you'd like if you have the room. But we'd say at x equals 1, f prime of x equals negative 2. And although that is very clearly what's happening right here, right, that's just listing out the point, we can probably do better. We can get more information of the graph of f. In particular, at x equals 1, f of x has a slope or derivative, whatever you'd like to use here, a slope of negative 2. And I can check that. Is that true? At x equals 1 on my original graph right here, is there a slope of negative 2? Well, certainly, because if I go down 2 over 1, I end back up on the graph. If I go up 2 to the left 1, we end back up on the graph. This is a steepness of negative 2. And so we might start to see then that this graph of f, when you look at its derivative should tell you all about the slopes of f, which is of course what f prime does. Right? If I wanted to look at this point over here, negative 3, comma f prime of negative 3, which is negative 2, I would read this as, at an x value of negative 3 on the graph of f, there is a steepness of negative 2. So knowing that, why don't you guys take a quick second, pause this video, and try to match up the other three. And I imagine you're not going to have too much trouble here. It's going to be a little harder to come up with an equation, so in fact I would ask you, don't come up with an equation, and instead just see if you can match it, and then hold in your mind how you would justify to someone why those match. So go ahead and try, and then unpause when you're ready. Okay. We are back in action, so let's just go through this. I mean, we might as well just go 2, 3, and 4. So let's look at 2. Right? This graph clearly has some sort of discontinuity in the middle. In fact, it looks like there's some sort of infinite discontinuity, right? There's nothing in the middle. So if there are no points in the middle, then when I take the derivative of any x value in this region, in this interval, then there's no derivative. We can't have slopes of points that don't exist. So I'm going to need that same gap on my other graph. And I don't see any gaps on A or B, but I do see that same gap on C. But then if we compare those two, it's kind of weird because this guy looks pretty darn similar to the left, but this guy doesn't look similar to the right. And can we see why that happens? Let's look at this from another perspective. If I put a bunch of points on this left side, what can you tell me about the derivative of the graph at each of those points? Or another way to phrase it, what can you tell me about the slope or the slope of the tangent line at each of those points? Well, hopefully you can say the slope, these lines, are all moving in a positive direction. So every value here, and I guess I should have done these on nice points. If we just take a look at this, right? This is, of course, the point when x is negative 2, f of x equals, well, I don't know. What do you want to call that? 0.25? Something like that? Cool. However, if we wanted to relate this to the derivative and make an ordered pair there, we'd say when x is negative 2, f prime of x is, I don't know what it is. It's not super steep, but it's definitely positive. And so that means that this point on f prime is negative 2 comma something positive. And so if I jump down to C over here, is this point negative 2 comma something positive? Sure, absolutely. In fact, all of these points have a positive y value, but we need to remember that the y in this case is f prime of x. So why does the graph drop down to the other side? Well, hopefully you've already answered that. But if you haven't, let's take a look at this graph, this second part of the graph on the right side. And let's now pick a point at 1. If I look at the tangent line to get a better idea of the slope, we can see that this point is located on a portion of the graph that has a negative slope, a negative derivative. So again, two ways to think about this point. It looks like the point 1 comma 1, which is nice. So at x equals 1, f of x equals 1. That's where we get the point 1 comma 1 on the graph of f. However, at x equals 1, f prime of x, the steepness, the slope of this is definitely negative. It looks like it's going, honestly, it kind of looks like it's going down 1 over 1, right? So, but it's definitely something less than 0, something negative. So this point on f prime has to be 1 comma a negative number. Let's see how we did. So if we jump down here, we see that this point is 1 comma a negative number. In fact, matching this up, it kind of looks like the point 1 comma negative 3. So what is that telling us? Well, it's telling us that on f of x, when x equals 1, f of x has a slope of negative 3. There's a negative steepness there. And that could confuse you because you're like, but wait, this graph is going up. You're right, it is going up. But it doesn't matter the slope of this graph. We care about the y values because this axis here, y-axis, is actually f prime. So every y value is a slope. And so if we jump back up over here, what we're really saying is that not only is this the point 1 comma 1, it's 1 comma 1 with a steepness of 3, down 3 over 1. The last two will do much quicker, I promise. Looking at this guy, we'll again approach it from another perspective. Let's look at those critical points. Can we see all the critical points on here where the slopes are 0 or undefined? Right? The tangent lines are horizontal. We know the derivative is 0. Well, if the derivative is 0, then that must mean that there are 4 points on f prime where the f prime coordinate is 0. And we should know then that anytime you have a point with an y coordinate of 0, doesn't that correspond to an x-intercept? And in fact, the one you guys probably picked on A up here, let's look at those x-intercepts. 1, 2, 3, 4 x-intercepts, right? This point, a little bit smaller than 2, a little bit bigger than negative 3. I don't know, maybe we'll call it negative 2.4, comma, 0. So what does that tell me? That means on f of x, so on the original graph, when x is negative 2.4, the slope is 0. And so if I jump back to this, is this coordinate approximately negative 2.4? It is. And is that point, does that have an approximate slope of 0? It does. The same logic, of course, goes with the rest of those. All right, let's hit our last one. This last one is kind of strange, but let's just talk about it in terms of slope. It looks like this last graph has a positive slope until approximately 1. And then 1, the slope is 0, which means f prime will have an x-intercept at 1. And then my slope goes negative after. So what does that look like over here? Well, if I jump back to my graph, notice that my line goes in a decreasing direction. My curve decreases all the way. Here's that x-intercept. And then on the other side, we continue decreasing. So how come all of this has a negative slope if we just said over here there's a positive slope and a negative slope? Oh, well, that's because the slope of f prime doesn't matter. The slope of every individual point here is positive. So that means that every x coordinate, we'll just take negative 1 for now, negative 1 comma whatever this is going to have a positive value. So the blue part of the graph that I've highlighted is a positive y value for every x on here. And that's why that when we look back over here, every y value is positive. This point, negative 2 comma a positive number, what is that, like 1.5 or something, is telling us that at negative 2 on the original graph, there is a positive slope. Versus this red one down here, we'll look at 2, right, 2 comma negative 3. This is telling me at 2 on the original graph, there is a slope of negative 3, a negative steepness. Whew. Well, there was a lot to that, so we should probably try a couple more. On the second page, there are 2 sets of 3 graphs, and I'm going to color them in just to make it a little bit easier on you. We have one graph that looks something like that. We have a second graph that's over here, and of course a third graph that's over here. Your goal is to decide which one of those graphs is f prime, and f double prime. And then once you've decided which graph is f, let's go ahead and look at all the critical and inflection points. And it's not red, or it might be red, I don't know. But either way, take about 30 seconds, look at those 3, and see if you can convince yourself as to which one is which. I'll wait. So hopefully you've decided which graph is which here. Now, what I hear a lot of people say is they go, well, this blue graph kind of looks like a cubic graph. So think x cubed. And when you take the derivative of x cubed, you get 3x squared, but an x squared. And x squared graphs look like this. And when you take the derivative of an x squared graph, 6x, that's a line. And so it seems like this is probably f, this is f prime, and this is f double prime. And in this case, you are right. We're going to talk a little bit more about making false conclusions like that. But for now, let's just go on the assumption that this blue graph is f. And let's start by identifying all the critical points on the blue graph. Well, the first critical point I see is up here, and the second critical point is down here. Those are the places where f prime is 0 in this case, or undefined. It's defined everywhere. And then let's see, what do those critical points look like on our other graphs? I'm sorry, I should have used a different color here. There we go. I'm using yellow because we're going to try to connect this to f prime. Well, if I kind of drop a point down, you'll notice I connect both there and here. And then same thing, I kind of connect over here. We can go up if you want. Well, if this is my critical point on f, on the blue graph, what happens on the other two? Well, on the yellow graph, the critical points are showing up as x-intercepts. On the red graph, the critical points are all over. So if you make the assumption that the yellow graph is f prime, which is the correct assumption, you might begin to tell, and we saw this on the previous page, that whenever you have a critical point on f, it presents as an x-intercept on f prime. And that shouldn't shock you because this has a slope of 0. And so this point down here, which looks to be approximately 1, 0, means at an x of 1, on f, the slope is 0. So we have to be very careful reading those points. So that's actually very helpful, though, because if we know where the critical points are, we know where the x-intercepts are of f prime, and vice versa. If you know where the x-intercept is on f prime, you know where the critical point is on f. We also talked about inflection points. So let's look at f. It looks like to me f is concave down until about here, and then it switches to concave up. So I'm thinking the inflection point is somewhere around here. What sort of connections do we have? Well, first, look at that. X-intercept on the red graph, which by now hopefully you're thinking is f double prime, and that is also not a shock. On the red graph on f double prime, that's the point 2, 0. So although you could say at x equals 2 f double prime is 0, you're right, but what we're really saying is at x equals 2, f has no concavity. Right? So interpreting the y value on f double prime is equivalent to interpreting f double prime. So as soon as you see this x-intercept, you go, oh, that's where the original graph turns into a line. That's where the original graph has no concavity. Or in certain cases, that's where the original graph switches sign, switches concavities, which means that actually this point is an inflection point. But even going further, notice that if I go down to the red or the yellow graph, that is actually a critical point on f prime. And that again should not shock you too much because, don't forget, although f double prime tells us about the concavity of f, f double prime also tells us about the rate of change of f prime. And so, if f prime has a rate of change or a slope of 0 as it does here, then it shouldn't shock us that its derivative, f double prime, will have an x-intercept. Isn't that what happened on f? When f had a critical point, a slope of 0, there was a x-intercept on its derivative. Same thing down below. When f prime has a critical point, then on its derivative you will also see an x-intercept. Last but not least, let's talk about those slopes, and I'm going to highlight in purple. Notice that my graph of f has a positive slope until here. Well, what happens on the graph of f prime? Well, on the graph of f prime, stopping there, the graph is above the x-axis, which should make sense because the y values are positive above the x-axis, which means the slopes are positive. If I continue further, now here is my negative slope, my negative derivatives, and if we look on our graph of f prime, notice that the negative derivatives are all below the x-axis. We have a positive slope over here, but that doesn't matter because the y values are negative. And then finishing this off, notice that f prime goes back up above the x-axis. As soon as we go above the x-axis, f starts to have a positive slope. And if we wanted to talk about concavity, we could. I'll do this in green. Notice that my graph of f is concave down until this inflection point. And on the red graph, which shows this concavity, the red graph is below the x-axis until the inflection point because the y values on the red graph correlate to the type of concavity on the original graph. These y values are negative, which means the concavity is negative. When f double prime jumps above the x-axis, that correlates to when the original graph is concave up. Positive y values of f double prime are concave up for our other graph. Okay, now that we have an idea there, let's go ahead and try this second one. Now, I'm actually not going to be as helpful on this one. And I'm going to switch up my colors too, so you don't think I'm doing the same thing every time. I'm going to give you this graph in green, and I'm going to try to do a better job drawing a straight line here. I'm going to give you a graph in blue and a graph in purple. Now, one thing you might notice is that I'm not giving you the graphs at the end. So I didn't tell you which color is which here because I think that spoils a bit of the conversation. So why don't you guys see if you can see what color is what, and also if you could label these three graphs, and then we'll go ahead and talk about the conclusions we should have come to. And we'll do this faster than the first time, I promise. So go ahead and pause me, see what you can do. All right, well, you might have drawn that same conclusion, and you might say, well, purple is the curviest of graphs. I expect purple to be f. Then we go down to a parabola, makes sense, and then we go down to a linear function as we take derivatives. That sounds good. But the real fun here is what are those three at the end? And before we get there, let's just look quickly at both a critical point and a change in inflection. Critical point on f, here's the first critical point I see, and notice that it does seem to correlate to an x-intercept on f prime. Nice. Inflection point, it looks like we change inflection here, right? We're concave down until there, approximately. And you'll notice that as I drop down, it looks like that does correlate to an x-intercept on f double prime. And also, double deal, it correlates to a critical point on f prime. Cool. Now, how do we talk about what happens at the end? Well, first thing we should notice is there is a sharp point right here. There's that cusp. And we know that when you take the derivative of a sharp point, when you see the sharp point, we say that a function is not differentiable because the derivative does not exist. So it should make sense that there's a closed point here. The original function does exist. But then when you take the derivative, that's our blue one, when you take the derivative, there's nothing because the derivative doesn't exist. And then when you take the derivative of that guy, there's also nothing because taking the derivative of nothing results in nothing. Another way to think about it is if you look at the slopes on this side, the slopes are all positive, versus the slope on this side is decidedly negative. So the slopes are all positive from here on up. And if you look at my blue graph, f prime is above the x-axis showing positive slopes. Well, then on the other side, and this is where things get good, if we assume that this is the rest of my f graph, and I'm going to go ahead and do that in purple, then think about the slope. That is a constant slope. It's a line. It goes down some, over some, down some, over some, right? And we know that when we do the derivative of this line, f prime needs to explain what those slopes are. These slopes are definitely negative values. Well, how negative? I'm actually convinced it's -1. Why? Because underneath there is a line at -1 on the y-axis, and there's also a line at 0. So choosing between the two of those, we have to think which of these two have y values that accurately describe the slope. Well, I think this does not have a slope of 0 like this first one because a line with a slope of 0 is horizontal. So instead, I think this guy is the continuation of f prime. Then how do we justify the last line, which of course has to be our green one, has to be f double prime? Well, we justify it in two ways. Option number one is we talk about the concavity of f. Lines do not have concavity. They have 0 concavity, which is why the y values on f double prime are all 0. But another way we could justify it is by talking about the slope of f prime, because f double prime is the slope of f prime, and this is a horizontal line. What's the slope of a horizontal line? It is 0. Now, do we have a way that we can kind of put this all together? Well, yes, I think we do. So this last part before we get into our summary is now I've just given you the graph of f. And what I'd like you to do is create two more graphs for me. I'd like you to create the graph of f prime and the graph of f double prime superimposed, so put over the top of this one. Now, my suggestion is actually to create a double sign chart. I think that's really going to help you. And then we can talk about what you're doing. So you are definitely welcome to give this a shot, or if you're a little stuck, you don't have to pause when I say pause, and you can just listen right along. So give it a shot, see if you can graph 2 more equations. If not, that's okay. Unpause me and we'll chat. All right, well, let's go ahead and tackle that double sign chart. Now, when I do a double sign chart and I'm given a graph, I really like my sign chart, the top of it, to match up to the length of this equation. I think it's going to be a little bit easier to just kind of put everything over. So I'm going to go ahead and just kind of make a little mark here and make a little mark here. And in fact, I'm actually just going to use the top of this, like so. Double sign chart, so I'll take up a decent amount of space here. Why not? We need a divider in the middle. And then we have 2 graphs we need to create. We need to create the graph of f prime of x and the graph of f double prime of x. And I'm just going to focus on one at a time. So let's start with f prime. Remember, f prime describes the slopes of a graph, and the dividers, I guess I could have put my x's up here, the dividers for this graph occur at critical points. So can we look at the graph of f and find critical points? Well, certainly. The graph of f has 0 slope at these 3 spots. It has no undefined slopes. I don't see any sharp points, no open circles, so just 3 critical points it looks like. My first critical point is, I don't know, between -1 and -2, so you could call it -1.5 if you want, or you could just put nothing in there and just divide it because it matches up. The next one is pretty clearly at 0, and then the last one is a little bit more than 1, just kind of following it down, something like this. Cool. Well, can we figure out the signs of f prime? I hope so, because the signs of f prime just describe the slopes of our graph. So as I trace my graph, what are all the slopes until I get to the first critical point? Those are all positive slopes. The graph is going up. Then we go down, and then up, and then back down to finish off. So looking at this, we have a pretty easy sign chart. Let's do the same thing for f double prime, and then we can see what the graphs look like. So f double prime measures concavity. That one's a little bit harder to tell, and it doesn't have to be perfect here. It looks like my graph is concave down until approximately here, and then we're concave up until approximately here, and then concave down to the end. So I think it looks like we maybe have 2 inflection points here. And again, it doesn't have to be perfect. You could say they're right on 1 and -1, whatever sounds good to you. But either way, there is going to be an inflection point, right here where the concavity becomes 0, and another one over here. What are the signs for f double prime? Well, because we're concave down, f double prime is negative, and then positive, and then negative. This is actually enough for us to get this graphed. Now I'm going to start with the graph of f prime first, because that's actually going to help us create a better graph of f double prime. So f prime, first thing we need to do, we need to remember that f prime, the output, the y values of f prime are 0 in 3 places. And whenever the output of an equation is 0, that is when you get x-intercepts. So here's one x-intercept, a second one, a third one. Notice it's just right underneath. And actually, I'm going to erase those so that I don't get too confused. The next part we need to realize is that if f prime is positive to the left of 0, so this is the spot that's to the left of 0 over here, then f prime being positive, again, these are the outputs. The outputs are positive. Well, what are outputs on a graph? Outputs are the y-axis. So essentially, this is telling you the y-axis is positive to the left of 0. So to make this positive, I certainly can't go down here. All the y's are negative. I think we have to come in kind of from this direction, don't we? Now, you can start to curve your graph. I know it's going to be a little bit more curvy just because I've done this before. The reason I know it's not going to be a straight line is because of this. If I make this a straight line, eventually I have to turn back around, and look at that. That's a sharp point. There's no way that something is going to create a sharp point from a smooth curve like this. So we're not going to have that. So what ends up happening is we're just going to have a nice little curved graph that comes in. Well, notice now I've crossed that critical point. I'm into the negatives. How long does my graph stay negative? Well, until my next critical point. Well, I can't just go here and then pick up at my critical point because there's a jump discontinuity, which again would only happen if there was some sort of weird slope thing going on, but there's not a weird slope thing. So what that tells us then is my graph actually needs to come back up and meet up over here. Perfectly? No, but meet up? Sure. And then we continue. I need to be positive until my next critical point. So something like this, and it's again going to do the same thing. And then I need to be negative to finish everything back off. There is a nice graph of f prime. Now, one way we can check to make sure we did this right is to compare this to f double prime, because this critical point on f prime where the slope is 0 is going to match up with our inflection point. How come? Well, here's why. F double prime becomes 0 at inflection points, right? It has x-intercepts the same way that f prime had x-intercepts at critical points. So if f double prime has an x-intercept right here and right here, notice that they both correlate to the inflection point and the critical point from f prime, because at its core, f double prime is just the derivative of the blue graph, and the derivative of the black graph gave us critical point, or gave us x-intercepts at the critical points. So the derivative of the blue graph will give us critical point, or x-intercepts at the critical points. And same thing over here. You'll notice there's a critical point directly below it. There is an x-intercept. Nice. To finish this off, we just follow the signs. F double prime is negative, means all the y values are negative till we get here. Then all the y values are positive till the next one, and then we finish off with all those negative y values. Whew. A lot to it, but hopefully it's really starting to cement the connections between. If it's not, that's okay. We have a couple more days to practice this. But what I'd like you to do now is to go through that same procedure, create your double sign chart, and make 2 more graphs on this guy over here. Once you're ready, unpause, and I'll go through it much quicker this time. All right, hopefully you guys had some success. Let's see how I set this one up. So looks like the edge of my axis is here and here. And then we have this one that jumps on over, something like that. Cool. -2 over to +2. We need to divide this out. Let's look at f prime. Critical points. 1, 2, and notice I'm already moving them to x-intercepts because I know that's what's going to happen. Okay, 1, 2, and 3. Slopes. Negative slope first, positive slope, negative, positive. Easy enough. And we're looking pretty darn good. Let's make that graph. When we do the graph, we know the y values are negative first, so they have to start below the y-axis. Then we have positive y values, so something like this, and then negatives, and then we finish off with positive y values. Cool. See how much faster that was? How exciting. And then we have f double prime. We build it based off of concavity, but if you want a different option, we can always look for the critical points of f prime, which means we're going to have an x-intercept here. And notice that does match up to our switching concavity. Doing it the other way, looks like we have a switching concavity right here. There's my x-intercept. It matches up to my critical point. Nice. I think that's about it. So let's see. Let's put in those critical points over here. Cool. And then what type of concavity? Concave up until the first one for sure. Then concave down, and lastly we finish with concave up. Can we graph this? Well, f double prime has to be positive at the beginning, which means we need to be above the x-axis. Then we need to be negative, and then we need to finish off with positive. People sometimes ask, how steep should my graphs be? And the answer is, we don't really have a good way to do that for now. You could try to analyze slopes and pick y values based off of that, but no one's going to expect you to do that. As long as you can get the right quadrants, really above, below the x-axis, and some curvature, you're fine. Now, I've been told that this next page is one of the most helpful pages for all of this unit. And because it gives a nice visual connecting different properties of f prime and f double prime. So I don't know if you want to star this page, make an extra copy of it, include it on your notes, whatever sounds good. Make sure it's in a quick section for you to turn to, because I think the first couple days you're going to use this a lot. Now, ultimately, it would be my goal that you really don't need to use this because you've done it so much, it's just second nature. Realistically, I know that that will not be perfect, but you'll definitely want to savor this page somewhere. So here we go. What we're going to be given is on the left something interesting about f of x. And on the right, we're going to see if this happens on f of x. And notice that I have the graph of f of x over here, and the graph is just what I'm doing in green right now. I have those dashed lines though, because the dashed lines just give you a good indication of where this point is on the next graph and on the next graph. So you just follow the dashed lines to see the connections between the three graphs. It does a nice job of splitting everything up here. So let's go ahead and begin. It says f of x is increasing. Now I'm going to draw in the increasing, the decreasing, all this fun stuff in different colors, and then I'm promptly going to erase it because I'm able to do that. And if I used 15 different colors, the graph would be unrecognizable. So I'm just going to do one at a time. It'll be much harder for you, so I would say maybe hold off on that. You can draw some arrows if you want, but let's just maybe match things up first, and then you can decide if you want colors. F of x is increasing. Well, for f of x to be increasing, that's where my graph is going in an upwards direction or positive derivatives. What does that look like on f prime? Well, this crossed over kind of had that dashed line as symmetry, so I think we have symmetry like this. And then also over here, there was a gap first, and then it was just after that dashed line. Well, how would you describe that? When f is increasing, what is f of x doing? Or f prime? And hopefully you're saying, oh wait, when f is increasing, f prime is above the x-axis. Very nice. So I'm actually going to do two things here. I'm going to say that f prime is greater than 0, which really means above the x-axis. And if you need more room, you can always use this extra line underneath if you'd like. But I'm putting two things. First, I'm talking about the sign, and then I'm also describing the visual. Now I'm going to erase this because my very next one says f is decreasing, right? Where f is decreasing, so that's going down, something like that. What is happening on f prime? Well, looking at f prime, the decreasing has this little gap before the first piece, and so to do that, I think we can just look at this part. And then the next one has symmetry about that dashed line, so I think that's going to be this part. And I imagine it won't shock you, the y values of f prime are less than 0, but of course visually that means that your graph is below the x-axis. Now that you see what you're doing, I bet you could probably go through and finish off the rest of this page. So why don't you try that? And then you can watch back through and just make minor changes as I go through it. They don't have to match mine exactly, but you can probably move much faster than I can. So go ahead and pause me, try to fill out the rest of this page, and then if you want to see all the pretty colors, unpause, and we'll go from there. All right, if you felt pretty confident on this, I'd say skip forward a few minutes so that we can do the bottom together. But let's go ahead and just run through the rest. All right. F has a local minimum. So local mins, I see two of those right there. What does that look like on F prime? Well, just kind of matching it up, right? We can see that it looks like my local mins are right here. So what does that mean? Well, first, we can state the obvious. We know that f prime equals 0, which is, of course, an x-intercept. However, we need to go further because this point right here is also an x-intercept, and we did not note that on f prime. So how could we, just by looking at this graph, realize that these two are local mins, but this one is not? Well, I think maybe we could talk about the direction f prime is traveling. Notice that f prime is negative, and then on the other side, f prime is positive. And I'm not talking about the slope, I'm just talking about the literal y values, the outputs of f prime. Negative meaning f prime is below the y-axis, and then positive meaning f prime is above the, I should have said x-axis the first time. And that holds true for both of those. This one does not work. This one, f prime switches from positive to negative. And so actually that's a very good way to describe this. So for f of x to have a local minimum, if you're looking at f prime, of course it does have to equal 0. It could also be does not exist if you wanted. But more importantly, we're going to say f prime changes from negative to positive. And we do have to keep straight that changing from negative to positive means below the x-axis to above the x-axis. And if you have room to write that, please go for it. Now, I assume we can figure out that the local max is going to be the opposite, right? Here's my local max, and the local max corresponds here. F prime changes from positive to negative. So f prime of x equals 0 could also be does not exist. It is again an x-intercept, but most importantly we recognize this because this is when f prime changes from positive to negative, or above the x-axis to below the x-axis. Continuing through, where does f of x have points of inflection? So we're erasing, and we'll switch up colors again. We'll go to that nice friendly orange. Point of inflection. Looks like we're concave up until here, then concave down, then concave up. I think our points of inflection are actually where I drew those dotted lines. Go me. What do those look like on f prime? Well, jumping down to f prime, right here, right here. Oh, well that's cool. So that means that f prime has local extrema, right? Either an absolute max or an absolute min. No, sorry, relative max or a relative min, right? So when we put these down, you'll notice that that corresponds to the relative extrema on f prime. So if you're just given the graph of f prime and you're saying, what is this? Well, that's an inflection point on f. Ooh. All right. What about where f of x is concave up? That's one we haven't covered yet. So I'm going to jump back to green because I'm out of colors. Concave up. Well, that's this section and that section. Well, looking on our graph, that's this section and that section. How would you describe those? Well, they're not just above and below the x-axis, right? They have two pieces there. Oh, what about the slope? Couldn't you say that f prime is increasing on both of those? And actually that should make sense, because if f prime is increasing, decreasing always is the derivative of this. The derivative of this is f double prime. So if f prime is increasing, f double prime is positive, but we'll get there. So all I think we really need to see here is f prime is increasing. And if you really wanted to put this, you could say positive slope, if that helps you out with what increasing means. Concave down is not going to shock you. When we do something that's concave down and I learn how to erase, we have that piece here, corresponds over here. When f is concave down, f prime is decreasing. Or you could think of it as a negative slope. Now, so far all we did was connect f to f prime, but we don't want to neglect f double prime. It's already two derivatives away. It feels lonely in its own right, so we want to make sure it feels welcome and connected. So here we go. F is concave up. Well, I did that in green before. I might as well follow. Concave up is here and here. What does that look like on f double prime? Well, following this all the way down here, I think it looks like that and like that, doesn't it? Again, actually, I'll even re-greenify these guys right here. So what does that look like on f double prime? Well, now it's not about slope. Up here is about slope. On f double prime, it's about the location. F double prime is positive above the x-axis for each of these. So if you were given a graph of f double prime and said, what does that tell you about f prime? You'd say, oh, both of these are above the x-axis. That's where f is concave up. Okay, so for f to be concave up, f double prime is greater than 0, which means above the x-axis. Again, hopefully not a shocker. F being concave down, I'll do in purple. Continuing that trend, negative slope or decreasing on f prime, but how do we describe that on f double prime? Oh yeah, that's where f double prime is less than 0, which means below the x-axis. Whew. Last but not least, we need those inflection points. So inflection point wise, I'll just do in red, make them jump out. Those are our inflection points, right? Jumps down here. Inflection points, those are the relative extrema, right? And at the end, inflection points, oh yeah, those are our x-intercepts. But remember, to be an inflection point, we have to do a little bit more than just be an x-intercept. So certainly f double prime is going to equal 0 or does not exist. However, if I had drawn a graph of f double prime and my graph looked like this, that is an x-intercept, but that is not an inflection point. These are inflection points. So what's the additional burden of proof put on an inflection point? Oh yeah, f double prime has to change sign. And at this graph that I drew in the middle right here, the left side of the inflection point is positive, the right side is positive as well. F double prime did not change sign. Versus here, f double prime on this side is positive above the x-axis, and then f double prime is negative below the x-axis. We did change sign. So two things here. F double prime of x has to equal 0, does not exist, and f double prime of x must change sign. And so when we say change sign, you could just say cross the x-axis instead of like bouncing off of it, right? This is a bounce, this is a cross. All right, this may help you out a bunch. I always implore you guys to just make a quick sign chart. I think you're pretty good at reading sign charts by now and it'll help you out. But either way, totally up to you. Save this page. We'll be coming back to it a bunch. But a quick disclaimer. Just because a function resembles a polynomial does not mean it's always a polynomial. So again, if you see a graph that looks like a parabola, x squared, don't assume that the derivative graph is linear, right? Derivative of x squared is 2x. You might say, ooh, parabola line. That's not always true. For example, we're going to look at f of x equals e to the x squared. I gave you both the derivatives, but I'm actually going to cheat on that right now. Take a look at what Desmos will do for us. Here's the graph of e to the x squared. Sorry, just a second. E to the x squared, right? Doesn't that look like a parabola? Parabola shifted up 1. And so if you looked at that and said, ooh, I know what the derivative is going to be. The derivative is going to be a line. Well, you'd be wrong. Because if you look at the next line, I've just typed f and then apostrophe of x. Desmos will read this as f prime of x. And if I turn this on, look at the derivative. That is not linear, right? That actually kind of looks like a cubic function. You're like, wait, did we do the derivative or did we undo? Like, did we do the antiderivative? What do we do here? Well, here is f prime. So you're looking at that, and you could maybe say, well, that's pretty close to a line. Okay, fair. What's the derivative of something pretty close to a line? Ha! Another parabola? Bet you didn't see that coming. And so, yeah, the derivative of e to the x squared does look like a parabola, but we don't want to assume that every derivative of a parabola is a line, because depending on the function, it might not be. All right, a little practice and we are done with this. Thanks for hanging in there with me. A lot of talking from me today, but strangely very little math, right? Just making connections. So some practice, and you should try to do this without looking at your chart up above. But if you want, if you get stuck, see if you can use your chart to help. If you know f of x is increasing, what does that tell you about f prime or f double prime? Well, let's see, if f of x is increasing, I think that tells me that f prime is positive, right? Because this describes the slopes of f. And so if f has positive slopes, f prime better be positive. If f of x is increasing, what does that tell us about f double prime? Well, actually, let's look at these graphs and see if we can actually figure anything out, because I don't even think we made that connection, did we? So let's see. Increasing, increasing. If we look at f double prime, this was the like increasing part and then increasing over here. I don't think it tells us anything about it, does it? So if f is increasing, then it really doesn't tell us anything about f double prime. It just tells us that f prime is above the x-axis. All right, second part. If you know f prime is positive, right, this means f prime of x is greater than 0, and decreasing. Oh, this is always the tricky one. If f prime is decreasing, then this is like the derivative of f prime. They're saying that the slopes are getting smaller. And the derivative of f prime that describes its slopes are f double prime. And that means that f double prime is less than 0. Ooh, that's always a tricky connection. So I think that's what it tells us about f double prime. It tells us f double prime is negative. Not that f double prime is concave down. That's a no-no. But what does that tell us about f of x? Well, it actually tells us two things, right? It tells us that f of x is increasing, and that comes from this part, and f is concave down, and that comes from this part. Because f double prime is negative, f is concave down. Because f prime is positive, f is increasing. last but not least, if we know that f double prime of x is positive everywhere, so f double prime of x is positive, what does that tell us about f and f prime? Well, you're looking at that, you're like, ooh, f double prime positive. We should know about f. F is concave up. That's easy, right? Positive second derivative, positive concavity. But what about f prime? Well, if f double prime is positive, then I think that's going to mean that f prime is increasing, right? And that's because f double prime not only talks about the concavity of f, it also talks about the slopes of f prime. And so if f prime has positive slopes, if f prime is going up, then f double prime is going to be positive. So let's go ahead and try to put that into two multiple choice practice problems. They're pretty similar to each other, nothing too terrible. And then you guys are done for the day. So the graph of a function f is shown to the right. Which of the following could be the graph of f prime, the derivative of f? They want to make sure you know what that prime symbol means. Very nice of them. So honestly, you should pause and try both of these. Neither of them are super tricky, especially based on what we just did. And then unpause when you're ready and we'll check those answers. Okay, graph to the right. We're looking for f prime. Here's how I break it down. Critical point, critical point. Those are x-intercepts. So there better be an x-intercept, maybe, I don't know, a centimeter to the left of 0 and a centimeter to the right. So this guy is out. That should have an x-intercept here and here. That one looks okay. This one's definitely out. That is 3 x-intercepts. That's a no-no. This one looks okay, and that one doesn't have any x-intercepts. That's definitely out. We're down to B and D. What else can we do? Well, f is increasing on these two intervals. Increasing, that's where f prime is positive. So if f prime is positive, that means f prime is above the x-axis. So if we look at those corresponding points, that's below the x-axis. That's a no-no. This is above the x-axis. Yeah, I think that's got to be it, right? Positive slope, positive slope, positive slope, positive slope. And then, of course, if you wanted to do the last part, negative slope below the x-axis. Cool. Last one. Hopefully you did okay, or if you want, you can always try pausing and try it again. Let's see what this one looks like. I'll start the same way. Critical points. Very similar problem, right? 2 critical points. That means 2 x-intercepts. That one's still in. This one has 2 x-intercepts. This one only has 1. That's out. It says 1, 2, 3. That's out. This has 3. That's out as well. Okay, very similar to before. We have a negative slope and a negative slope. So those red pieces have to be where f prime is below the x-axis. Above the x-axis, we're out. Below, below. Whew. Now, today was all about if you have f, what do you know about f prime and f double prime? We had some other bonuses in there, but that was really the main theme. Because what we're leading up to is the most common free response question that is served on every or appeared on every AP exam since 1969. It is the guarantee that there will be something like this, and instead of them giving you the graph of f and asking about what do the other graphs look like, they go a step further. This is calculus. We're not going to be dealing with the graph of f. We are going to be dealing with the graph of f prime. So next class, it's all going to be, here's a graph of f prime. What do you know about the graph of f? So instead of working, I think of this way as forwards as we did, of taking these x-intercepts over here, we're going to work backwards. We're going to say, ooh, x-intercepts, those are going to be critical points. But I think it's always nicer this way. It makes a little more sense to start with f and work down, as opposed to next class where we're going to start with f prime and work back up the ladder. Thank you as always for your hard work and participation. I'm going to go ahead and sign off, and I'm excited to have you guys back for next class.